Moving on to 5.3, we're going to use what we just talked about to define what's called a definite integral. We define a definite integral using the Riemann sum, what we just did, where we let the partition subintervals approach 0 as in the previous example, just like we did. So we let all the rectangles get super, super skinny. Now, there's a special notation for this, and you will see this in like one homework problem. This is just saying the width of the rectangles is getting smaller and smaller and smaller until it approaches 0. It's called a norm, this notation, and it's just describing the width of the rectangles. So notice this is the same formula, but instead of like n go to infinity, this is basically saying the same thing. It's just, instead of using the letter n, it's saying let the width of the rectangles approach 0. Which means let n go to infinity, meaning let there be infinitely many rectangles. The more rectangles you have, the skinnier they have to be. The definite integral exists, this being the definite integral, when we always get the same limit j, no matter which choices are made for a partition or the point ck. So whether you use the left-hand endpoint, the right-hand endpoint, or the midpoint, you end up with the same answer, then that's going to be called the definite integral. So there's a history. I don't know how to say this guy's name correctly. Leibniz notation. Leibniz introduced a notation for the definite integral that captures its construction as a limit of Riemann sums. He envisioned the finite sums becoming an infinite sum of values f of x multiplied by infinitesimal subinterval widths dx. So our delta x that we've been talking about was the width of our rectangles. We're letting that go so small, we're going to start thinking about that as a dx instead of a delta x. They're going to be switching places. So in his notation, the sigma notation is replaced by the integral symbol, which originates from the letter S for sum. Please don't draw an S. It is not an S. It is an elongated S with a straight line in the middle, curl at the top, curl at the bottom. F of ck is replaced by f of x, representing a continuous selection of function values rather than a finite selection. Remember, we're letting there be infinitely many rectangles, so every single x value is now going to have a rectangle. And that is too many x values. There are infinitely many x values, so we just do it in general for x. We don't worry about the k anymore, the ck. Delta xk is replaced by dx, representing a very small width for our rectangle, small change in x. It is as if we are summing all products of the form f of x times dx. So our height times our base, as x goes from a to b. Think of this as the area of each rectangle for every possible rectangle from a to b with infinitesimally small width dx. You don't have to get all of this. You just need to have a little bit of a vague idea. That's pretty little. Alright, so if the definite integral exists, this being the definite integral, this is how he's saying we can write it. We can write it as the integral from a to b of f of x dx. So if I write this notation right now, I simply mean do what we did on the previous problem. That's it. So this previous problem over here, we could have written in this format. Why not? Let's go do it. So in this problem, the formula would have been from 0 to 2. The integral from 0 to 2. Our f of x was 4 minus x squared. And then we put dx. This notation means do all this mess. For now. Alright, so some terminology for you to describe these. These are what we call our limits of integration. So lower limit goes at the bottom, smaller number usually, but it could switch as we move through integration. So lower limit of integration, the upper limit of integration. By lower and upper, we're just saying this is at the bottom, this is at the top. The small and big could switch. This is called the integral sign. The function is called the integrand. Dx is telling us which variable to integrate with respect to. Just like when we did implicit differentiation, we had to say derivative with respect to. We have to tell who to integrate with respect to. And then, let's see. That's the integral. Yep. All right, let me go to my next. That's not my next one. This must be my next one. Open whiteboard. Maybe. Pause while it thinks about it. Okay, so now we're going to have the discussion about right hand versus left hand versus midpoint. we can pick the point ck to be any point in the subinterval. Doesn't even have to be left, right, or midpoint. It can be any number, as long as it's inside the base of that rectangle. As n goes to infinity, all of the locations of ck will have the same limit. What? Well, think about it. Your rectangle has a base. As n goes to infinity, that base gets smaller and smaller and smaller, which means the left-hand side and the right-hand side are getting closer and closer to the midpoint, and then they just end up all being mashed together because you end up with 0 width. So they all end up becoming the same value in the limit. So our formula, this guy here, can be written out specifically for right endpoint case as follows. Now, this formula here, if you want to memorize and use it, you can. This is actually what I showed you. So this right here is just your delta x. And this right here is just your delta x. So this is the formula I wrote out earlier. This is your ck. A plus k times your delta x. That's your ck. Times b minus a over n. That's your delta x. So we already talked about this formula earlier. You do not need to memorize this formula, but you may see it in homework. It would be helpful if you memorize the ck formula that we talked about in the 5.2 section when we did the Riemann sum. It would make it easier, but you can figure it out without it. Most of you. Some of you are going to be better off with the formula. It just depends on how your mind works. All right, properties of definite integrals. Order of integration. So remember I told you that we can switch the limits of integration. It doesn't have to be the little number on the bottom and the big number on top. It could be either order. If you switch the order of integration, all that does to the answer is changes the sign. Okay, so make sure you put it in the right order or you're going to get the wrong sign. Now, if you integrate from a to a, well, that's your x values. If you integrate from a to a, that means you haven't gone anywhere. You can't have any area if you haven't actually got a base to integrate over. So that's why this has 0 area. It's because you haven't integrated anything. You're just integrating a straight line. There's no base, no width. Constant multiple, if you have a number multiplied by your function, that can come out. Just like with summation notation, just like with derivatives. The constants just chill out. Sum and difference, if you have things adding and subtracting in a definite integral, you can do them separately and then just add or subtract as appropriate. Additivity, all right, look, this is integrating from a to b, and this one picks up at b to c. The insides are the same. So instead of integrating from a to b and then b to c, you can integrate the whole thing in one shot from a to c. Sometimes it is useful to break it up, and we're going to talk about that, especially in Calculus 2 when you need to be able to break it up. For here, we're just going to play around with a couple of cool things. So what I want to do is I want to give you 3 values. So notice I'm not telling you what the function is. I'm just setting it up, the integral notation, and telling you the answer. And I want you to use these values to find the following definite integrals. So if we were to integrate from -1 to -1 function f of x dx, what's the answer? Pause, take a minute and think about it. Well, this is the rule when you integrate 0 width interval, a to a. These two are the same values. So because you're not integrating any width, the answer has to be 0. The integral from 4 to 1. Well, they told us the integral from 1 to 4. So what's the relationship between these two? Notice the f of x is inside. We have integral from 4 to 1 and 1 to 4. Well, we talked about that this, if you just change the limits of integration, it just changes the sign of the answer. So it's negative what we already know. So negative, and that was a -2, which makes this a +2. So the negative changes the sign because they had the integral in the other order. All right, so here we have a sum. So like we said, if you have the integral of a sum, you can break it up and do the integral of each piece separately. Don't forget to put your dx after each one. Now, the integrals they gave us don't have a 2 and a 3 inside, so we still have to adjust so that we can get what they gave us, or use what they gave us. So remember, if you have a number multiplied by a function, that number can come out. So this is 2, the integral of f of x dx, plus 3, the integral of h of x dx. Now, they gave us the value of the integral of f of x, from -1 to 1. Sorry, let me put my limits of integration. And they gave us the integral of h of x from -1 to 1. So let me go over here and look. So f of x from -1 to 1 is 5, and h of x from -1 to 1 is 7. So 5 and 7. So this ends up being 2 times 5 plus 3 times 7, or 10 and 21 make 31. All right, one more. So the integral from -1 to 4 f of x dx, what did they give us? They gave us the integral from -1 to 1 and from 1 to 4. So how do we use these two to find what they're asking us? Well, because we stop at 1 and then we pick up at 1, the inside is the same. It says in the additivity, all we have to do is add the two answers together. So 5 and -2. So this is the integral from -1 to 1, f of x dx, plus the integral from where we left off, all the way to 4 f of x dx, which is 5 plus a -2, or 3. Make sure I got my numbers right. 5 and -2, yes. All right. So those were some examples using the properties of integration, definite integrals.